Okay, so let's continue our discussion related to amplifiers. And in the last lecture, we had seen that if we have an ideal transistor, then it's very easy to construct an amplifier by simply connecting the voltage that we want to be amplified to its input and connect a load resistor at its output. But ideal transistors are not available, and we were looking at how to take care of the various non-idealities that may be present in a practical transistor. And in the last lecture, we had seen that suppose the relationship between current and output current and voltage follows this particular behavior, where the current is zero until a particular threshold is crossed, and after that the current begins to increase linearly with Vi. And the output current versus output voltage is like an ideal transistor here. And then we had seen that in order to take care of this non-ideality, we have to bias the transistor using this particular bias voltage here and RB here, such that the transistor operates in this particular region here. And in order to avoid DC voltage going to the load, we had used a capacitor here to block the DC so that only the signal that we apply goes to the output here. And to provide a DC path, when we are biasing it, we require a DC current to flow through our element X. And this one resistor was added to provide a DC path here. And this kind of an arrangement was used to apply a voltage to the input of the element X here, which is the sum of Vs plus Vb here. And we had seen that these are in cases where one terminal of both Vs and Vb is ground. So we cannot simply stack one on top of another to add up the two voltages. We have to use an arrangement in this particular manner here. So let's add some more non-ideality to our hypothetical transistor here. So let's look at an element Y, which has this non-ideality here, that the current is zero below a threshold voltage here. But besides that, it also has non-ideality in the output characteristics here, that the output current is independent of output voltage in this particular region here. And below a voltage equal to, let's say, V saturation, the current is actually zero. And in the negative direction also, the current is zero here. All right, so remember, in an ideal transistor, I naught is independent of V naught and is of this particular nature here. So we have two non-idealities, a non-ideality which was present earlier also, and which we know how to take care of. But we have an additional non-ideality in the output current versus output voltage here. So if we compare this characteristics with this, we know that if we want to use our device Y as an amplifier, we'll have to operate somewhere in this particular region, obviously, because in this particular region, then the output current is zero, and obviously will not get any amplification. So we have to, push our device into this particular region here. All right, so will our earlier solution work? The earlier solution was of this kind here, right? So will this solution work for a device like this here? Well, let's evaluate. So this is the biasing arrangement that we have here, okay? So let's look at whether this particular arrangement will work. Now note, as we just discussed, in order for our transistor, for our device Y to amplify, we'll have to operate somewhere here above threshold voltage, and we had seen issues related to what is an appropriate biasing voltage here. So we'll have to operate somewhere here. And similarly, on this characteristics I0Y versus V0Y, we'll have to operate somewhere over here. So what we are saying is that this is the bias point for our device here. Bias point, or we had discussed earlier, is also called quiescent point or Q point here. So we'll have to push our device Y. We'll have to operate it at this particular place here. And once we operate it at this particular place, then when the signal comes in and it goes through my device here, it will get amplified and appear over the output here. Okay, so, and we had also seen, so we have two kinds of voltages and currents in the circuit. One is the DC bias voltage here to operate it at a particular Q point. And the other one is the signal voltage here. So we had said that the analysis of these amplifier circuits can be divided into two parts. One is a bias point analysis to figure out where is the Q point, and the other one is the analysis related to the signal, also called the AC analysis here. So if we look at the DC circuit here, the capacitors are open circuits, so the DC circuit is shown over here. And so if we look at this case here, well, we have applied voltage which is larger than the threshold voltage here, so that's fine. So we are somewhere over here, but this requires a current to flow, and the current to flow in this direction here. And then this results, the current of course has to go like this, and then this results in a negative voltage here. Now, which is contradictory to this particular plot. It says that if you're anywhere less than VSAT, VSAT is positive here. Anything less than VSAT here, then the current is 0 here. So this thing is not going to work for us, because this arrangement will give rise to a negative voltage here. So note that if we are to use a device like device Y to work as an amplifier, we'll have to, so this is fine. If we are applying a voltage more than the threshold point. So from the input side is okay. From the output side, we'll have to maintain this voltage as positive. Note that voltage has to be larger than VSAT, some positive voltage here, let's say 1 volt or 2 volt or something like that here. So we'll have to maintain positive, and this arrangement doesn't allow us to have this particular voltage positive. So to create a positive voltage with a current flowing like this here, and we have to provide a path for DC current to flow here through a resistor. So what we need to do is add a DC voltage here, positive voltage here. So if we add a positive voltage here, VDD, let's say here. Now, if the voltage is sufficient and the current is flowing here, and the current flows like this here, we can have a positive voltage here. And depending on the value of RD and VDD here, we could make sure that our device Y is operating at somewhere in this particular region here, whatever is the desirable Q point, we can ensure that a device operates there through the selection of RD and VDD here. So our circuit then modifies to this kind of a circuit here. So we have the earlier arrangement of VB, RB, VS, CG, everything remains the same, except that we've added this positive voltage here, supply voltage here, to push our transistor or our device Y into this particular region. Okay, so we can redraw this particular circuit in this form here. Okay, same thing, redrawn with RD taken up and VDD taken like this here. And very often we don't show VDD with a with a voltage source like this, positive and ground here. We often draw it in this particular form here. We draw a bar here saying that the voltage at this point is VDD, which effectively means that we have connected a voltage here between this source and ground equal to VDD in this particular manner here. So whenever you see a bar like this and with a symbol attached VDD, it effectively means there's a battery connected to ground with a value equal to VDD. All right, so this is the revised schematic that we have, and this should help in amplifying here, because this arrangement of VB, RB and VDD, RD will help to ensure that my device Y is at this particular Q point here. And after that, the signal will go through and will get amplified here. Okay. The other one is, if we look at this particular schematic, we are using two DC voltages. One here to bias to make the voltage larger than threshold voltage here, and another one here. And so the issue is, why unnecessarily use two DC voltages? Can we bias using one single DC voltage only? And so using only, let's say VDD, using only VDD, can we bias, can we incorporate the effects of VB and RB? And the answer is simple, yes, we can do that. Note that the effect of VB and RB is nothing but to generate a DC voltage here. Well, we could do that through this particular means here, VDD here, and we could build a voltage divider R1, R2, and that would generate a DC voltage at this particular point. Okay, we are of course assuming that we'll choose VDD, which is larger than VB here. Okay, and so VDD is chosen as larger than VB, and therefore the value of VB that was going here as DC voltage here through R1 and R2 voltage divider. So it is easy to see that VB will be equal to VDD, R2 by R1 plus R2. So by suitably selecting this ratio R1 and R2, we could get the same effect as this VB and RB that you see. Okay. All right, so that becomes our revised schematic here. A schematic of an amplifier using a device Y here. So this arrangement, again, this of use of VDD and RD is to create a positive voltage at this particular point so that we operate here. And the arrangement of R1 and R2 through VDD is to create a positive voltage greater than V alpha so that we operate somewhere over here. Okay. All right. So let's further add some issues with our device. And so we are taking this sort of an abstract approach and gradually adding more non-idealities to arrive at a device which will look more like a transistor. And therefore, the amplifier schematic that we would construct would then be suitable for the real transistor also. So in this case, we have a characteristics very similar to what we had in device Y, except that what we are saying is that I0 versus Vi characteristics is very sharp. There is a threshold, but is very, very sharp here. And the reason why we are saying this is, for example, if we were to look at a bipolar transistor, and in a bipolar transistor, this may be base and this may be emitter. And between base and emitter, there is a diode. And we know that there's a certain amount of voltage that is required to cause significant current to flow. Maybe the voltage is about 0.7 or so. And the diode characteristics is exponential. It's very sharp. So basically, to look at what are the consequences of a very sharp characteristics, let's look at this device Z here, which is the same as device Y, but with a very sharp characteristic. So this is the amplifier that we had here, right? This is the amplifier that we have here. And this is the characteristics. I0Z is equal to 0 for VOZ less than 0.2. So this is 0.2 here. For anything less than that is 0 here. For anything greater than that is a constant. And then it depends on the value of VIZ here, input here. So for VIZ less than 1 volt, threshold less than 1 volt is 0. And for VIZ greater than 1 volt is 1 times VIZ minus 1 here. So note that if you go to VIZ equal to 1.1, then the current flowing will be equal to 0.1 into 1. So is 0.1 into 1 is 100 milliamperes. So very large current. The moment you go a little bit above V alpha, you get very, very large currents to flow here. Okay. So the point behind the trouble with this particular circuit is when you have very sharp characteristics like this here, is that the circuit is very sensitive to variations in resistor values, power supply, device parameters such as V alpha. Why? Because this I0 versus Vi characteristics is so sensitive. Small change in Vi will result in very large change in current. And as a result of this, the circuit is sensitive to everything else. For example, R1 and R2 will decide what is the voltage applied here, the DC voltage here, right? So any small change in R1 or small change in R2 will cause a small change in voltage here, but then that would cause a very large change in current here. So that's not something which is good here, all right? Because these unwanted variations in R1 and R2 or unwanted variations in VDD will cause a huge change in the characteristics and the current flowing, and that's not something which is desirable here. As an example, suppose we take VDD equal to 5 volt, R2 equal to 1K, R1 equal to 3.95K, and then VIZ is equal to 1.01 volt. All right, so if we put in these numbers, we'll get 1.01 volt. And then 1.01 volt, we have this equation here. We get output current is 10 milliamperes. All right, so 10 milliamperes. Now note that a small change in R2 by basically 1%. R2 is 1K here and R2 is 0.99K here. So small change in R2 causes VIZ to go to 1.002 and output, and this current, DC current, becomes 1.9 milliamperes here. So a small change of 1% change in R2 is causing a huge change from 10 milliamperes to by more than a factor of 5. So this extreme sensitivity of the circuit is not very good. Similarly, for example, if R2 were to go to, let's say, 0.98K, from 0.99K to 0.98K here, then VIZ goes to 0.994 and output current actually falls to 0 here. So this very large sensitivity of this circuit to circuit parameters is something that we need to address. Otherwise, this I0Z versus VIZ being very sharp will create a problem. Now note that this very sharp characteristics is good for us in other ways. For example, if this characteristics is very sharp, it effectively means that I0 is very sensitive to Vi. which effectively means that the transconductance is very high. And we have seen earlier that the voltage gain is nothing but product of transconductance and RL. Product of transconductance and RL here. So a high transconductance is desirable. But a high transconductance, which means very sharp characteristics here, brings in all this sensitivity here. So let's solve this problem of sensitivity here. And one solution to this particular problem of sensitivity is to add a resistor here. Earlier, this particular terminal was connected to ground, and let's add a resistor at this particular point here. And let's analyze this particular circuit. So let's do a DC analysis. So DC analysis, all these capacitors are open here. So we get effectively a circuit like this here. VDD, R1, R2, RD here, and RSO here. And in general, a circuit like this, note that we can redraw it like this here, VDD, R1, R2 here. And then what we can do is we can build a Thevenin's equivalent between this node and ground here. Thevenin's equivalent of this particular circuit. And so Thevenin's equivalent would be open circuit voltage here, which is nothing but voltage divider. And the Thevenin's resistance would be resistance looking left of this particular part, which is R1 parallel R2. Right, so we can describe it by a Thevenin's voltage and a Thevenin's resistance here. Thevenin's resistance being R1 parallel R2, and Thevenin's resistance is nothing but voltage divider here. So DC circuit becomes like this here. All right, so let's continue. So DC circuit is like this, and this element Z that you see here has this characteristics. From input side is open circuit here, and from output side is a dependent current source with the value Gm VIZ minus V alpha. The moment you are greater than V alpha, this is the current flow here. So let's take this model here and plug it here into our circuit. So this is what we obtained. Okay, and then let's do a KVL here. Let's do a KVL here. Let's write down the equation. So minus Vt plus, note that there is no current flow here, plus Viz here, plus Iz0 RSO equal to 0 here. And note that since I0 versus Viz characteristics very sharp, so although Viz will differ from Vt, but will differ from V alpha, but because it's very sharp, as an approximation, Viz will be almost equal to V alpha here. Just like when we take a diode with an exponential characteristics, it's very sharp. We know that the diode voltage drops, diode voltage changes, but we take diode voltage equal to 0.7 or so. So in this case, we are taking Viz equal to V alpha equal to 1 volt here. So I0Z then becomes here Vt minus V alpha by Rs0 here. And note that basically the current is decided by this expression here, and the current is no longer very sensitive to parameters there. The current depends on whatever is the bias voltage that you apply here and whatever is the current here. And if for some reason, let's say you change R1 and R2, note that Vt depends on R1 and R2. If R1 and R2 change by 1%, the variation in Vt would be 1%, and you can see the variation in I0Z will also be around 1% here. So the sensitivity of the circuit is brought down by connecting this RS0 here. So we now have I0 dependent on this particular relationship. Earlier when RS0 was not there, then the current was dependent on Viz, and Viz was equal to Vt. So a small change in Vt would result in the change in Viz, and because of the sharp characteristics, a very large change in I0 would occur. But now, because we have connected this extra drop in this particular loop here, and then the current is practically determined by this particular expression. It's no longer determined by this sharp characteristics. So sensitivity of the circuit to various parameters is reduced considerably if we add this particular resistor in this particular path here. And now my circuit, my bias point, everything will become very, very stable because of this particular feature here. Okay. So this becomes our revised circuit here, right? So gradually we are adding more complexity to a circuit to address various issues that are there here, right? So we started by adding RD and R1, R2 and capacitors here, and now we've added RS0 here. All right, so let's analyze this particular circuit. So DC analysis we've already done. Let's do a AC analysis. So when we are doing AC analysis, the capacitor will become a short because the impedance of the capacitor, we are saying at the frequency of interest, is very, very small. So that's why we are taking it as a short. Any DC voltage will become shorted. So remember, there's a DC voltage here connected to ground, so that will become a short. That's why this is ground here. So this is a circuit that we get here. And we can simplify it. Note that this point is ground, so R1 is effectively in parallel with R2. RD is effectively in parallel with RL. So we can simplify the circuit in this particular manner here. And then this is the model here. This is the model for this particular element. And we had seen earlier that Gm times V alpha is a DC part here, so we can ignore it. So this is the AC model of this particular element here, our element Z. So let's take this element out, put in the AC model here. So let's do that. Let's replace it by the AC model shown over here. And we get the circuit here. And now it's easy to analyze it. Let's write a KVL here. Vs will be equal to Viz plus Gm Viz Rs0 here, the drop here. That's the second term here. The drop here is nothing but this current multiplied by Rs0 here. And V0 is nothing but this current multiplied by RD parallel RL, so V0 is here. And we can solve these two equations to show that the voltage gain is minus Gm RD parallel RL, 1 plus Gm Rs0 here. All right, so this is the voltage gain of this particular circuit. All right, so let's compare. This was the original circuit. This was an original amplifier where we didn't bother about where the characteristics of Y was not very sharp, and so we didn't bother much about the sensitivity. And the gain of this particular circuit was Gm RD parallel RL here. Now we have a device Z which is very sensitive, which has very sharp input characteristics here. And so we had to add a resistor Rs0 here. And so by adding a resistor Rs0, we could reduce the sensitivity of the circuit to R1, R2, VDD and all the other things that are there, make the circuit much more stable. But the gain has fallen. The gain is now GMRD parallel RL same, but is divided by 1 plus GMRS0 here. So if we plug in some typical values, we'll see that this GMRS0 would be larger than 1. And in fact, if we put in some typical values here, if we try to design it, we'll find that if the gain is, let's say, 100 or so here, the gain becomes something like 2 or 3 here. So the gain becomes considerably smaller. So we have solved one problem, but in the process, we have lost the gain here. The gain becomes very small because of this term in the denominator here. And but then that's fairly easy to solve. Note that gain that we are talking about is an AC gain, depending on the AC voltage here and the AC input here. And this term is arising because there's a resistor Rs0 here. So note that if we connect a capacitor across it, then under AC condition, if the capacitor value is large, this Cs, 1 by omega Cs will come in parallel with Rs0. And if this 1 by omega Cs is very small, effectively, then Rs0 is shorted out, right? And therefore, we will get a gain which is equal to the earlier value, which was minus Gm RD parallel RL here. The term in the denominator will go away. While under DC condition, capacitor is an open circuit, so Rs0, its effect would be there, and it would continue to make the circuit stable. So we have achieved both. We have made the circuit stable by including Rs0 here, and by bypassing it through a capacitor like this, bypassing this particular resistor through a capacitor, under AC condition, the effect of Rs0 is reduced here, or practically eliminated here. Okay, one last problem. So let's now, so far we had seen characteristics which were after crossing the threshold, they were linear, and this part also was linear. So now let's add a characteristic which is non-linear here, right? So there is a threshold here, below threshold current is 0. And after that, the characteristics is, let's say, non-linear, and various kinds of non-linearity can be there. So let's say, starting with, let's say, a square law here. I naught is k Vn minus V alpha square here for some Vn greater than V alpha. And some value here, V alpha is 1 volt and k equal to 0.02 here. We have taken this square law because if we look at a MOSFET, in a MOSFET, the current versus voltage characteristics would follow something like this here. If we were to take a bipolar, then we would have taken an exponential here. All right, so this is our circuit. Right, so this is the circuit that we had arrived in general for something of this particular sort here, right, to solve those problems. And let's look at how this particular circuit will behave when we have a non-linearity like this here. Okay, so remember, for amplification we wanted a linear characteristics. We wanted output to be of the same shape as the input, except that it's a magnified version. But now that we have a non-linearity, let's see what the consequence is. So let's say VB is 1.5. VB means we've chosen R1 and R2 such that this voltage at this particular point is 1.5 volt here. And let's add a Vs equal to 0.3 volts sin omega t, the voltage that we are amplifying here. So this is our I naught versus V in characteristics here. Okay, I naught versus V in, same characteristics that we have, same characteristics we have plotted here. And we are biasing it at 1.5 volt here. Okay, 1.5 volt here. So now we apply a total input would be the sum of the biasing voltage, 1.5 volt is DC, plus on top of that we have a 0.3 here. So 1.5 to 1.8 it goes, and 1.5 minus 0.3, so 1.2 it goes here. So that's the net voltage here. So what would happen is this is the biasing point, and the voltage will go a little bit above and a little bit below, and therefore I naught will vary. Because of the sinusoidal part, the I naught will vary here. So the I naught goes like this here. There's a DC value of I naught. Note that the DC value will be corresponding to 1.5, about 5 milliamperes. So the DC value is 5 milliamperes here. And then because of the AC signal here, I naught also executes the signal here. But note, you can see that even though the input is a perfect sinusoid, the current is not a perfect sinusoid here. Why? Because the characteristics is nonlinear here. So when you go from 1.5 to 1.8, when you go here, the current increases because it's a square law, the current increases more. Then when you go from 1.5 to 1.2 here, the current doesn't decrease as much. And that shows up here in the distortion in the output current here. And if the output current, note that the output current is here, the output current of the device Z. If we were to draw the AC circuit, the output current would flow through a parallel combination of RD and RL. So V naught is nothing but related to minus I naught, the AC part of the this part here, multiplied by RD parallel RL. So if you were to draw V naught also looks like this here. So V naught is also distorted. And so this is the consequence. Because it's nonlinear, my output voltage is now distorted. And is distorted, and therefore our amplifier has a problem, because we wanted output voltage to be a perfect sinusoid, to look exactly like the input. But now because of nonlinearity, there's a distortion. There's a distortion because we are biasing it at a particular point, and when the input voltage is going up, the current is increasing a lot more in the positive direction, and when the input voltage is going down, the current is not decreasing by as much here because of this nonlinearity there. So waveform is distorted. Now, however, that's something that we cannot do. Whenever we have a nonlinearity, the distortion will always be there. However, if our input is reduced to 0.1 volt sin omega t, so earlier it was 0.3, but suppose we have Vs equal to 0.1 volt sin omega t. This is what the output looks like here. If we were to plot, the output looks like, and now you can see the output is pretty good, seems like a reasonable sinusoid here. So the idea is that distortion will be much smaller if you restrict the input voltage to a very small value. Note that the output voltage doesn't have to be small. The output voltage, look, the output voltage is pretty large here. The AC output voltage is almost like 2 volt here, minus 2 peak value here, plus 2 or around that particular value here. But the input is, because that's where the nonlinearity is there. Nonlinearity is there. So if you restrict the input to a very small value here, so note that even if a graph is nonlinear and you are at a particular point, and if you restrict your variations to a small region here, then the small region could be approximated by a small linear segment here. So that's the idea, that if the input is small, then the nonlinearity doesn't bother us so much, and we get a linear, reasonably undistorted output voltage here. So our amplifier will work properly with small distortion if we restrict the amplitude of the input signal to a small value. And that makes sense also, because we are building an amplifier to amplify a small voltage. And so the signal that is coming in from a microphone or a video signal is typically a signal which is a weak signal here. And therefore, when it's a weak signal here, and therefore the distortion associated with it is would be pretty small here. All right, so let's stop here. So now what we are seeing is that if we have a device with the characteristics in this particular manner here, I0 versus output current versus input voltage, nonlinear with a threshold here, and output current versus output voltage in this particular manner here. Well, we could, make a amplifier in this particular manner, which would amplify the small voltage that is applied here. All right, so let's stop here, and then in the next lecture we'll see that we are now ready, that all we need to do is take this element Z out and put in a MOSFET or a bipolar transistor. And because a bipolar transistor or a MOSFET, we'll concentrate mostly on MOSFET, and we'll show you that a MOSFET characteristics is very similar to this kind here. So we can take this out and put in a MOSFET, and the device will amplify. All right, so let's stop here.